Okay, so then let's start today's class. So let's first see what we have done so far. So basically we have learned bifurcation, and we have seen by how by transcritical bifurcation first of all. So these, let me go toward the bifurcation diagram here. So we have seen by transcritical bifurcation, first of all, at r equal to 1, this extinction become unstable, and a point which is existence becomes stable. This part for r greater than 1, this part becomes stable. Now, as our intuition says, since r means the growth rate, per capita growth rate of the individuals, so as r increases, the number of individual in that population that will survive will actually increases, as it seems that x star, that the fixed point, the number of individual that remain in the population after a lot of iteration, means the ultimate fate of the population is existence. And if the reproduction rate increases, per individual reproduce at a higher rate, the number of individuals which will be remain in the population is increasing with r. You can see that x star is increasing as r is increases, as this is as our intuition says. But what our intuition does not say us, or does not conclude that, so after r equal to 3, you will see that it is not the case. For r equal to r greater than 3, there actually this existence, the single point existence become unstable. And what happens there? So there the population become oscillating. So oscillating between two states, oscillating, suppose for r equal to, suppose r equal to somewhere here, r equal to something. So here r equal to some, you will see that the population will oscillating between these two states. So one state is this point, and another state is this point. So this is quite non-linear, since this happens because of the non-linearity in the system. So you see now the population oscillating between these 2 points, this point and this point. Now this remarkable thing that happens at r equal to 3 is called the period doubling bifurcation. From here the period 1 to, it becomes every period 1 point split into 2 and become period 2 point. And we have numerically and mathematically checked by through algebraic equation. We have seen that for this range, for second, for 1 to 3, the x star equal to r minus 1, that is stable. And for these 3, that when the bifurcation occurs, when r remains in between 3 to 1 plus root 6, the ultimate fate of the population is that population is actually oscillating between two states, one is x0, another is x1. That we have learned so far. Now, as we are hinting, I have hinted in the previous class that if I increases further, suppose now 4, if I increases further 1 plus, what happens to the system? Now the question is, what happens to the system? Will it oscillate between 2 points, or the every 2 points, means x0 and this x0 point and x1 point, both will become unstable, and x0 will divide into 2 point, and x1 will divide into 2 point, as in the case of this first case, where only 1 point was there, x0, and it divide into 2 point, one become x0 star, one is become x1 star. This is called the period doubling. Now will it be the case that if I increase furthermore from 1 plus root 6, will it the same thing happens? The answer is yes, the same thing happens. The 2 period become 4 periodic orbit. So if I increase this, so it become fourth period. And to calculate it mathematically or analytically, it is very tough to calculate, but we will see in this class that we can see numerically that it is actually happening. For if we increase the r values of r, the growth rate from 1 plus root 6, that every uh, every point of the two period, that is x0 and x1, will split into further 2 points, and it will be x0 x1 and it will be x2 x3, and the two period orbit will cease to exist. Now this two period orbit become unstable, and what is born in the system is the four periodic orbit. And you will see in the Stoger's book that there is a list of value. So 1 plus root 6, from if r 1 plus root 6 to root 6, if so is less than 3.54409, so up to this much, up to in this range, it will remain 4 period. Now if I increase furthermore, so if I increase r, suppose 3.54409, if I increase furthermore, it is not exact number, there are so much numbers in between. So if I increase further, what happened? uh, Subodhaji, is it clear that means it is not clear, means my argument is clear, but you will see that from means mathematically showing, theoretically showing, it is very means near to, means very hard, but we will see in the later on the class that we can see from the bifurcation diagram by using the computer that two period orbit actually become four period orbit. We will see. Now you can guess that as it happens in the previous case, and here also uh, every point, four period orbit means there are 4 points, they means orbit with oscillating between these 4 points, x0 x1 x2 x3. Now if I increase further, what happens? Every point will split into 2. Now you will see there will be a 8 period orbit, and this 4 period orbit will become unstable, and new 8 period orbit will become stable, and it will be stable. And how much, how longer it will remain stable? That is 3.5644. 3.5644. Then at 6, that 3.5644. If I increase further, it will become 16 period. Okay, this is 8 period orbit. This is 8 period orbit. Now they receive 3.5644, and 5, this is 5440. Okay, this is 5 6 something 789. So there is a number, so up to which you will see this will become 16, and it will going so forth, so on. So every time we increase a little bit, the period doubling happens. Every single point will split into 2, and it will become, so first it will become 2 period, then it is 4 period, then it is 8 period, then it is 16 period, then 32 period, and it will continue so. And at last, at r, it's called r infinity, at r equal to 3.569946, there will be infinite periodic orbit. So at first it seems mind-boggling, how could be infinite period orbit will appear. Means it says that you will have a infinite points through which the system will go, and it will oscillating between this infinite point. So I can give an example, so it is not quite that hard to imagine how the infinite orbit is. Suppose, give an example, so suppose there is a continuous line, so between suppose 0.4 to 0.8. So suppose there is a continuous line. Now you see in between point 0.4 to point 0.8 how much point is there? Infinite number of point is there. And if it is infinite number of points, suppose the orbit trajectory will be such that it is continuously, it's not it's continuously going from point 0.4 to point 0.8. That means it, in each time it will increase via means it actually visiting all the nearby points. Then you can see that suppose the system will going like this. First of all, this go like this, and then it just came back in this direction. So it is a periodic motion, but you see that in the this periodic motion, in oscillation, there are infinite points through which the system goes. So the infinite periodic orbit is quite easy to visualize, that any continuous line, if anything moves in a continuous manner, that will be actually infinite, that could be thought as a infinite period orbit. That's all. So is it clear, Subhusaji? Okay, now what happens? Now one thing is very important to see, that means means the discoverer of the logistic equation, that who is the first person who realized that through logistic map these complicated dynamics could be realized, whose name is May, and he was a population biologist, and he first of all in means it is quite humorous that he had written in a corridor of a board that it is his phrase, what the Christ happens for r greater than r infinity. So it is phrase that what is actually happening if I increase a little bit further. Suppose if I increase from suppose I take an r which is r greater than r infinity, what happens then? No, the answer is the dynamics become quite complicated. Now the dynamics become quite complicated, and it turns out that these complicated dynamics actually is called the chaos. This is actually chaos. Now why chaos? And we will see in the means I left that part for the last 3-4 classes of my this but there we'll see that by mathematical theorem that this system has actually contained chaos, because we already know to prove the chaos there are according to the definition it has 3 components. One is sensitive dependence of the initial condition, second is transitivity, third is infinite a lot of periodic orbit. So that is actually we can see last part is we can see that at r equal to infinity there are infinite periodic point are there. So that we can see from here that there is quite large number of periodic orbit is there, and all of the periodic orbits become unstable. That's the thing. So one thing you may notice that whenever from if I go here from here it will be more clear. So whenever I am saying that these become stable, that doesn't mean there isn't a fixed point at x star is equal 0. X star is equal to 0 is remain a fixed point, that become unstable. And here also it remain there but it become unstable. Similarly, when the fourth period appears, these two period does not cease to exist, they exist but their stability change, they become unstable but they are there. So you see that the last condition that is required for the satisfy to definition of the chaos, that there will be a lot of periodic orbit, that is actually satisfied, because you see all these periodic orbits, that 2 periodic orbits, 2 periodic orbits, 4 periodic orbits, 8 periodic orbits, 16 periodic orbits. So it's, if I write that 2, 4, 6, like all the periodic orbit actually there for r greater than r infinity, for r greater than r infinity, but all the periodic orbit remain there, that 2 period, 4 period, 8 period, 16 period, 32 period, 64 period, infinite period, but all the periodic orbit will loses its stability and become unstable. So that last part of that definition of the chaos is satisfied. Now what was where was I? I was lost. So where was I? So it was quite complicated. So the dynamics were quite complicated. Why it is quite complicated? Because they have seen that uh, there are large values, there are many values of r greater than r infinity, where there are no there are no stable attractor, no single, okay, there are means r greater than r infinity, the sequence, we know the orbit or orbit, which does means the sequence of, as we define the sequence of xn, that if I iterate infinite times, that sequence become the orbit. So orbit, for there are many values of r equal to r infinity, the orbit never settles down to a single fixed point or a periodic orbit. Instead, the long term behavior become aperiodic. The long term behavior become aperiodic. So you see that in the previous case, suppose from here, if I go back here, so here, so you see for r less than 1, the system's orbit actually settles down to where? At x star equal to 0. And if I go from beyond r equal to 1, it settles down to this point, this x star equal to r minus 1 r. And if I go further, it become periodic orbit, 2 periodic orbit, then 4 periodic orbit, then 8 periodic orbit. Eventually, you will see it become periodic, but when r greater than r infinity, when r greater than r infinity, a remarkable thing happens, which is that the orbit or this sequence of xn actually never settles down to any fixed point or any periodic orbit. It actually become aperiodic and roam in the phase space and quite erratic manner. So it is called the chaotic orbit. So let's see, as we know already how the chaos looks like in this if I plot the iteration. So let's see again, it is quite fun to see the chaos. So suppose we choose a parameter value r equal to 3.9. Suppose actually what we are doing, let me write it what we are doing here. So we actually want to plot this xn, the sequence of xn, and we know that xn plus 1 equal to r into xn 1 minus xn. So suppose we are going to suppose we are going to suppose some x0. What x0 I have taken here, suppose here I have taken x0 equal to 0.4. Now point x0 equal to 0.4. Now if I write it x1 equal to r is 3.9 into 0.4 into 1 minus 0.4. So in this way, by putting the x2 value, so x1 value x1 into 1 minus x1. So putting this way, I am going to plot 150 values of x, 150 values of x. So let's see what is there. So okay. Yeah, you see that this is the chaos I am talking about. That you see these points are quite not repeating itself, and there is no pattern at all, and they are never settling down to a any fixed point. Instead of, if I put here, if I put suppose uh, let maybe let's less than 1, suppose 0.5, r is 0.5, what we expect, it will go towards, yeah, it's, you see that this trajectory go towards 0. Now let's put here, suppose let's see a two periodic orbit, suppose 3.1. You will see that there is a two periodic orbit. So here every time it go and it remain in the two periodic in that thing. So this is two periodic. Now let's see at means you will see in this way that at, if you see at, suppose in, let me show you a four periodic orbit, suppose 3.5. Let me take a 3.5. It will, you will see at 3.5 it become a four periodic orbit. Yeah, it, you will see that there is a four periodic orbit. Suppose this point and this point and this point and this point, this is four period, and again it comes here. So first of all this and here, so it comes again here. So 1 2 3 4. So it going it's oscillating between these 4 points, this red dot, this red dot, this red dot, and there is a point, I am here is a point. So between these 4 points, this actually trajectory is oscillating. So this is a 4 periodic orbit. And suppose, and if we increase a little bit in suppose 3.9, you will see a remarkable thing happens, that all periodicity vanishes there and it suddenly become aperiodic and it becomes chaotic. So this is the chaos. So now let's see it in as we know cobweb diagram. So let's see the in the cobweb diagram how it looks like. Yeah, this three. Okay. So let's see how it looks like in cobweb diagram. So you see that the point actually it's look quite complicated, and it actually same thing that we have seen in the previous picture. So that the pattern, the point will not repeat itself. So previously we have seen that this point actually oscillating between these 2 points when the period 1 point become period 2 point. Here you see that the point will never settles down to a single point. It will go here and there, and this kind of motion will continue to be remain in this region. So this is called the chaos. This is we mean by chaos. That's how the chaos looks like. It's become quite aperiodic and it moves randomly between the points. Now that's it. Now Subhusaji, is it clear? Okay. So these root means there are, so let me first clear here one thing. So there are three root known to us by which a system can go to chaos. First route is means first, and why what we are studying here, it's the period doubling route. Period doubling period doubling route. Then there is a intermittency that we will study here. Intermittency route to chaos. And then third one is that quasi periodic, through quasi periodic orbit. And we have seen some example of the quasi periodic orbit in this class, but we will not go details of the quasi periodic, means how chaos appears in the quasi periodic orbit. So means I can simply say in the quasi periodic orbit, when the trajectory cut itself, then the chaos appears. So it's quite complicated, so we will not go into the quasi periodic zone, because it's a clearly it's means the system has to be means it actually naturally we study this quasi periodicity in for the system of Hamiltonian system, where the energy remain constant, and it is quite fascinating in the quantum chaos also, the quasi periodic chaos. So we will not go deeper into quasi periodicity. We will only see these two kinds of chaos. One comes from the period doubling route, and one is intermittency route. That period doubling route we have already seen, and we will prove mathematically why this chaotic ones, those those three conditions actually satisfied by this logistic equation. Now another way means why, what is the motivation of this class is this another way to see the chaos. First of all, we have seen the system, but there is means there is no way to say, means there is a way to say the chaos in the later we will see. Now there is another way to see that the chaos is appearing on the system for a large values of r. So here we have seen for only single values of r, what we have seen for the single values of r, for a single values of r, we seen the system is looks like crowding. Now we want to see something, we want to generate something which will give a pictorial representation of the chaos for a large values of r, means for a range of r. So that thing is called the orbit diagram. That we will that in this class we will learn how to draw orbit diagram. This is called orbit diagram, or it is also called the bifurcation diagram, that we have learned bifurcation diagram. So that we have already seen in the previous lecture, that how the bifurcation diagrams looks like. Now we will use a computer, since the mathematics behind these things become complicated. If I go from 2 period to 4 period and 4 period to 8 period, it becomes horrible. So let's use computer by showing this orbit diagram. Now what will we do? So first of all, what orbit by orbit diagram, what we want to know? We want to know that what is the long term behavior. What we will see, the long term behavior, long term behavior of the system, means where does the system goes? Does it goes to a single point, or does it go to a 2 points? It's oscillating between 2 points. So suppose at some values of r, the system, if I iterate multiple times, and we will see at last the system will settles down to 2 period orbit, one is x0 and x1. Then what will be the long term behavior of the system? You will see for that particular r, the system actually, suppose this is in the y axis, if I draw in the y axis the point where the system remains. So you will see that the system will oscillating between these 2 points, and the long term behavior will be the system will appear here once and then here. So this kind of thing I want to collect these 2 points x0 x1 and draw these 2 points for suppose r. So I can say that this x0 and x1 is the long term behavior for these particular values of r. Is it clear that what orbit diagram is? Yeah, bifurcation diagram and orbit diagram is same, but means to generate the bifurcation diagram through computer is quite complicated. That's why we will generate the orbit diagram, and you will see that orbit diagram is exactly looking like the bifurcation diagram. So let's see. Okay, then what we will do, first of all, we iterate n equal to for 1000 times. Suppose we are iterating the system 1000 times. That means we are collecting x0, x1, x2 and x1000. Okay. Now what I will do, for suppose r equal to, for every r, for each and every r I will generate this sequence. Now for r equal to some particular value, suppose r equal to 3.1, what I will do, so in the y axis, suppose in the x axis I will plot this r, and in the y axis this is the long term behavior. So suppose point r equal to 3.1, what I will do, I will plot last 300 sequence. So that means from x equal to 701, x 702 and x 1000, I will plot last 300 points for 3.1. So I will get suppose 701 here, 702 here, 701 here, x 701 here, x 702 here, then again that x 703 will be near about these, and x 703 will be near about these, and at finally you will see that these 300 points actually remains very close to these 2 points. So we can say that the ultimate fate of the system will remain between close to these 2 points. So at r equal to 3.1 we can say that the long term behavior is the oscillating between these 2 points. So that's all we are doing. So I have written down a code for this. So that is, let me show you the code. Okay. So that is actually bifurcation diagram. Okay, you see that number of iteration, here I am going to the 1000 iteration. So number of iteration is 5000 iteration. Total number of iteration, how much iteration I am doing. So I am collecting first x1, x0, x0 until x 5000, and I am collecting last 500 values of this. So that means I am collecting 5000, 5501 to 4501 to 5000 data, and I get the last 500 data, and I will plot that things against the r equal to that value. So if I do so, what will get? Let's see. So first of all, we will not generate all the things, then it will be, first of all, let's do it from 0 to 1. So if I plot 0 to 1, what do we expect? So Bhusaji, if I plot here from 0 to 1, what will be the long term behavior? If the values of r remains between 0 to 1, what is the long term behavior? Right, fixed point 0 extinction. You will that's great. Okay, you will see that that is actually happening. Let's see. you will see that this black dotted line, so black line, can you see that line, or it is it's not visible? This black line, if you see that black line in 0, so that means the long term behavior is the extinction, it remains 0. Now let's see if I increase, now let's see if I increase 0 to 3, right, 0 to 3, and what will happen now? It should go to, yeah, so that is the case. So that is the bifurcation diagram that we have seen. So its long term behavior is, first of all, from 0 to 1 it remain in between 0, then where it actually goes, it goes to some existence, and that point actually increasing as r, as we are increasing r. Now if I increase further r, what will happen? It should bifurcate between 2 points, and it oscillate between 2 points. Let's see whether it's, or whether or not it is happening. Let's see at 3.2. Yes, indeed, it is the case. So as you can see, this is the quite look like the bifurcation diagram. So first of all, it goes from 0 to 1, then it goes from here, then it bifurcates between 2 points. So not the system will remain in a single periodic orbit, it becomes 2 periodic orbit, because at r equal to greater than 3, suppose it is 3.1, the system's long term behavior remain close to between these points. That means it is actually oscillating between these 2 points. Now let's see if I, and we know how long it remains stable. So we know that it remains stable up to 1 plus root 6, so np dot square of 6, so that much, up to that much it will remain stable. And then suppose, now let's see, draw a 4 periodic orbit here. So let's do a, suppose r3 is 3.5 up to okay, up to 3 point, suppose 3.55, let's do that, 3.55, 3.55. now you see, you will see 4 period orbit. Okay, let's see, this is a 4 period orbit is after this point. So this point is basically, so if I draw, you can see it clearly. So what is this point? So it is nothing but 1 plus np dot square root of 6. Yeah. Now you can see that these I have drawn that np dot square root of 1 by 6 by doing algebraic equation. We know that after 1 plus root over 6, if r greater than become r greater than root over 1 plus root 6, then the 2 period orbit stability changes, and it previously it was stable. Now if I increase further, it become unstable, and you can see that every single point of the 2 periodic orbit split into 2. So first of all, these split into 2, and this also splits into 2. Now the system's long term behavior becomes 4 periodic orbit. So systems oscillating between suppose 1, 2, 3, 4 periodic orbit. So that's how we actually draw the orbit diagram, or you can say so this is a bifurcation diagram. Now this is not so important because we want to see the chaos in here, so we will plot from 3.4, because in the these means out of that range, we know already that things. So we will generate suppose 3.4 to 4.0. Now you can see how the chaos looks like. So first of all, what does we expect previously to by, let's us guess what it will look like when the system will become chaotic. So what does chaotic means? Chaotic means it will never repeat itself. So that means no systematic thing you will see. Here previously you see that it actually oscillating between these 2 points. So this is suppose x something x1 star. This is suppose x2 star. So oscillating between these 2 points. So that's why you are getting these 2 points. Now chaos means it will not never oscillating between these 2 points. What it will happen, so you will see a lots of point, actually last 500 points. So you will see 500 different points, because last 500 points should not be equal to each other. If suppose if suppose any point become equal to, suppose in the last, suppose is 4501 to x 5000. So suppose that x 451 is actually become to x 4850. So if it equal to this, that means the system will become periodic. Means after that much value, the system will should repeat itself. But since the system has no periodic orbit, it become aperiodic. It could not be the case. So this could not be the case. So that means every point should be, no point in this region should be equal to each other. That means you will get 500 different points in between, and when the chaos will appear, you will see a dense points, a dense collection of points, not a single point or not a 2 point, not a 4 point, but a dense collection of points. You will see these kind of thing when the chaos appears. So this is our intuition. Let's see whether or not it is appearing or not. So let's see. Aha. Yes, indeed. What we intuitively see, that is actually happening here. So let me draw first that thing, that R infinity. As we know, as our R goes beyond R infinity, the chaos will appear. So that means let first draw a line, red line, similar to the previous case, that R equal to infinity. So what is R infinity? R infinity means, as we know, that R infinity is x equal to 3.569946. So you see that if I further increase the R, you see there is a lot of dense point here, lot of dense point here, lot of dense point here, lot of dense point here. What does this mean? This means the 500 points are different from each other. So the system actually not going to any stable attractor. It's actually roaming in between infinite points. So the sequence never settles down to any single point or any periodic point. Previously you can see there are actually points. This is showing, this is 1 2, this is 4 period, 1 2 3 4 period. Here 1 2 3 4 5 6 7 8. Now you see after when R become infinity, the system become chaotic. That means the system's actually source is it's actually roaming around between infinite points. Now that's another way to see the chaos. So this is called the orbit diagram, and it is actually trademark of the chaos. If any nonlinear dynamics book, you will see these kinds of picture. And now you know how to draw the bifurcation diagram for anything, or orbit diagram for anything which it is very important to know long-term behavior. So this actually the numerical methods of doing drawing the bifurcation orbit is very important. So that's all. Is it clear, Sobhusaji? Exactly, 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 exactly. That is happening here. So previously, what you see that at any suppose r equal to 3.5, r equal to 3.5, you see that clearly the system's long-term behavior is actually this 4 period. The system remain close to this 4 period, 4 points. One, two means if I draw a line, you will cut this curve in 4 points, and that 4 period is the system's ultimate fate. The system will remain close to that 4 points. But here, when you see the dense points, you know that you cannot know that actually the system remains, means systems are closer to which points. System actually close to many points, so the system become means the predictability loss, and it become means predictability loss, and the system become chaotic. So that's the one thing. Now, the interesting thing is what happens. So you see, after r equal to r infinity, the systems means where this white zone. If you see this white zone, in the white zone means in between white zone, you can see in between white zone, as you see, as you say that in between this chaotic region, that's dense or points, there are a single white zone. So in this white zone, the system become again periodic, and the predictability comes because here you can see only 4 points are means in the white region, 1 2 3 4 5 6 7, only you can see there 7 periodic orbit appears. And here also you see 1 2 3 4 5 6, 6 periodic points are there. So in between means this the system, if I increase r greater than r infinity, the system will interspread between the chaotic cloud dots and periodic windows. These are called these white regions are called periodic windows. Now, what is the another interesting thing is that we are getting one larger periodic window, that is here. Can you see my cursor in the screen, Sobusaji? Okay. Uh-huh. So, you see, this is the larger periodic, or this is the larger periodic window. Every white is called the periodic window. Now it is the largest periodic window. So you see here the largest periodic window. What is happening here? So suddenly a periodic orbit of 3 appears. So 1 2 3. So in the previous cases we have seen that only two means the whatever the period is actually multiple of 2. 2 period orbit, 4 period orbit, 6 period orbit, 8 period orbit, 32 period orbit. Now for the first time there are 3 period orbit appears at near about its point is 3.83. So it is 3.83. So it is actually near about 3.83, a large periodic window window appears window appears. So and the period of the system becomes 3. You see here. So if I draw any line, how much point it contain? 1 2 and 3. So the system will remain close to 3 point. That means system is oscillating between these 3 points. So this is actually a 3 periodic orbit. Now we will see how the 3 periodic orbit actually. Now let's let since the time is not there, okay, let's see how much we can do. So let's see actually by graphically how this 3 periodic orbit appears by and so as now, so far so good. Now let's what we want to do. We know at near about r equal to 3.83, a new periodic orbit born whose period is 3. Now we want to see how the 3 periodic orbit is born there. So and we will see only graphically, because the mathematical things we can do mathematics, but it is quite it is very hard to see. So and this is here to see. We will show you that I will show you that r equal to 1 plus root 8, there is a saddle node bifurcation, and we see what the saddle node bifurcation. What is meant by saddle node bifurcation? We have seen that. So let me recall that saddle node bifurcation. What does it mean? So you will see out of the blue, out of the nowhere, you will see two fixed point appears. One becomes stable, one unstable. So one is stable, one is stable, one is unstable. So previously, if I r is less than this r star, so there will be no fixed point. When r become or equal to r star, you will see two fixed point appears, that is stable or unstable. And as we from the definition of the three periodic orbit, we know if some point is if there in the system three periodic orbit exist, this condition means then we have to solve this equation. X star is equal to f q x star. Three periodic orbit is nothing but it repeats itself after three iteration. So that means x star should come back to its initial point x star if I iterate the x star with three times. So that is called three period orbit. So if I draw fqx, so how to means, as we know, how can we calculate the fixed points? So suppose here it is a fx. So how should I calculate the fixed point? So I want to draw, means anyone will draw a line that is called identical line, that is y equal to x, and wherever this point cuts, so this point and this point, these are called the fixed point. So to exist a three periodic orbit, this identical line should cut this fqx function three times. So is it clear how, means as you know, means is it clear that how one should calculate the fixed points by graphically? So let's see. Okay. Maybe it is in the Coburg diagram. Maybe in the Coburg diagram is there. So I am doing nothing. You see that here I am defining that function gx equal to that map fx. Actually, if you see r equal to x into 1 minus x, and what is fq? Here if you can write fqx is that three times iteration of f of x, that is here. So let me yeah. So this is this okay. Now I draw it for, okay, draw it for, suppose let's draw it for r equal to 3.835, okay, or r equal to 3.82, r equal to 3.82. Oh, now you see where 3.82 is very close. It's 3.81. Let's do it 3.81. 3.81. Okay. Now you see where does this fq cut? So here you see there are 2 points, actually 3 points where fq cut. So one is what? One is 0, one is this point, and one is this point. So these 3 point fq cut. Now does these 3 points, actually not these cuts here, actually it's cuts in 2 points. One is this and this. Now you see these 2 point is nothing but what it is? It is actually the point of this is the fixed point of fx, the single period orbit. Since let me calculate here. So if x star equal to fx star, suppose there is a x star which is equal to fx star, then if I apply f 3 time here, suppose f of x star will be f of f qx, that means f of x star. So f of x star means f x star, so this will be x star, and f of x star means x star, and f of x star means x star. So that means if any point satisfied this equation f of x star equal to x star, that will also satisfy this equation x star equal to f qx. So that means any fixed point of fx or the which is single period orbit, every single period orbit will be a 3 period orbit. So the 2 point that you are seeing here, so one is this, another is this. These 2 point actually corresponding to the fixed point of f star equal to means the period 1 orbit. This is not the period 3 orbit. When the period 3 orbit will appear, you will see when these values sink, these value also sink, and these hills above this point, above this gray looking curve, this is identical curve. When suppose for example, take this valley, when these valleys sink down, and some point you will see that it will cross the line, and it will cross the line. So if I draw here, suppose this valley is now looking like this. Now if I increase further, you will see that this valley will cross the point here like this, and you see there will be 2 points will be born, one is this and one will be that. Okay, I doing it reverse now. Okay, these and this. So you will see like that. If I increase, and when means first of all, first it will not cut, it will first become the tangent, and when it will become the tangent of the this valley and this hill, it is called this in case of saddle node bifurcation, you know that it first become the tangent, then it becomes cut the point. So let's see. So we know that at 1 plus root 8 in p on square root of 8, it becomes the tangent. Yeah, well, now you can see what I am saying, that this identical line become tangent to every this valley and this hill. Now if I increase further r, this valley will sink down further, this valley will sink down further, and this hill will grows upward, and you will see every this hill will cut by 2 points, this hill will also cut by 2 points, and this will also cut by 2 points. Let's see. So if I increase further, suppose if I increase to 3.835, and you can see here its value is 3.828. Now I want to 3.83. Let's go to 3.835. 3.835. Now what happens? Yeah, now you see that system is actually cutting these two by every point, means there are in the previous there was no fixed point at all. Now you see that the 6 fixed point appears, and you will see here, you will see that you just this become fixed point, and it actually goes to the fixed point and it remains there. So that means this is a fixed point. Now the cobweb diagram is not roaming around, it actually goes here and it's remain fixed there. So that means there is a stable fixed point. And you see this comes from a saddle node bifurcation, and every here where you will see 2 points are there. These points actually, let's say for example this valley, so these points, so here this, if you draw the slope, if we draw the slope, this is steeper, so here this point is unstable, and here this point will become stable. Here also this will become stable, this is unstable. Here also this will stable, when 2 points are there, there will be 1 point is stable, 1 point is unstable. This is called the saddle node bifurcation. By the saddle node bifurcation, you will see that there will be three stable fixed point, and the system will roaming around between these three fixed points. Now is it clear? Subhusaji, is it clear the three periodic orbit? Okay, so if it is clear, then in the this is called, actually we know that this is saddle node bifurcation. Out of blue, 6 fixed point appears. So in the previous in the next class we will see it again, then it will be much more clearer maybe. So let's end this class now. Then we will. Okay. Hmm. Hmm. Huh. Hmm. 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 Okay, but hmm. Hmm. Yeah, the quantum chaos itself means the term is very fascinating. But to know the quantum chaos, you have to take a class of quantum. If you know the quantum mechanics, then I can start, because otherwise it is pointless. But I will say something in general. If I see something, if I can read something general about the quantum chaos, I can means I will tell you. Okay, let's see. Hmm. 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 Yeah, yeah. Hmm. No, I haven't heard about these things, but it exists. They exist in the field. I know. Hmm. Hmm. Huh. Hmm. Hmm. Yeah, yeah. Huh. Hmm. Hmm. Huh. I uploaded, but after the class it will be available in the YouTube. So you will heard the means. Okay, I will share the link, but the means in terms of uploading I am lagging behind. Means I have uploaded only 8 videos, maybe, or 8 or 7. I don't know. Maybe 8 or 7. I will upload all the video. I will upload in the YouTube. Hmm. Fine. Hmm. Huh. Yeah, I will. I will send everything. Okay. Okay. Thank you. Next Friday, right? Yes. Okay. Okay. I am ending this class here.